At this point, you now are understanding how to find the z-score, and you've now been introduced to the idea of being able to understand when you have a normal distribution, the probability of being below that point or being above that point in the distribution. So now here's 3 more examples I want you to try out. I'm going to walk through them really quickly, but I want you to try them on your own first. So if you're following along, this would be a great time just to pause and see if you can do it. And then the next slide, we're going to walk through how to actually do that here. All right, so if you had the chance to do it, the steps for the first one, we'll walk through that. So we're asking what is the probability that someone is more than 1.63 meters tall with the distribution we've been working with. So now, to get the z-score, we plug in the value, so 1.63, minus the mean, 1.4, divided by the standard deviation. That gives us our z-score, which is 1.53. And then we can go to the table. If we look back, we can look at the table for the z-score that corresponds to 1.53. It's not shown here, but in the back of the book, in the appendix, you'll be able to find this. And you'll see that the probability of being higher is 0.0668. Now similarly, when you ask the question less than, we're still going to find the z-score, going to find where it is, and this time we're getting a negative z-score. So our z is negative 1.33, which tells us we're now below the mean. So here, when it's negative, the table, you can find the positive value of that. So you find the positive 1.33 in the table. And then you can look at how much is above it. And that is, it's like the mirror image of what we're seeing here. So what above positive 1.33 is this, which is going to be the exact same as what is below the negative 1.33. This last one, the between question, so we're asking what's the proportion between those two heights. So we have 1.63 and 1.2, which we already found, so we know the amount below that point and above that point. So to find the individuals that are between, what we can do is find how much is left. So we can add these two up and do 1 minus those two, and that's going to give us this result, the 0.8414. The other approach to doing that is saying what is it between this point and the mean, which is 0.4082, because it's just this. So it's half of the distribution, which is 0.5, minus this, which gives us the 0.4082. And then on the other side, from here to the mean is this value. So we got 0.5 minus this, and that gives us the 0.4332. When you add those up, that gives you the same value as adding these two and taking that away from 1. So when we have a normal distribution, this is the information we can get. We can get more than just the z-score. We can get the z-score in any distribution, but in a normal one, we can use the z-score to find the probability of being higher or lower than points or being between points. So I recommend trying this out, just like the last one, and seeing if you can solve it on your own. As before, the answer is right here. I'm not going to walk through it this time, but I want you to think through this and see if you can solve it. All right, so back into the theory. We just went over a lot of examples showing how we can find a z-score and how in a normal distribution the z-score can give us more information about the probability. But now we need to talk about the difference between parameters and statistics. And when we're talking about the population, generally we're talking about parameters. So mu is a parameter. Sigma is a parameter. From a sample, which again is just a selection of individuals from the population. So if we want to understand students at Utah State, we might just get a sample of students, just randomly select students from a grand list of students and get information from them to understand how the rest of the population is. So in a sample, it's called statistics. These are summaries of information. Core ones are n, which is the size, how many individuals you have in there. X bar, which is hard to see here, but that's the mean. S squared is the variance, and S is the standard deviation. When it comes to what is called statistical inference, that involves using information from a sample to draw conclusions about a wider population. So we're using a subgroup, just a sample, to understand how the broader population is. So one of the issues of using a sample is that different random samples are going to yield different statistics. And that's just due to random sampling. So one sample might have a few more people with higher values. Another sample might have a few more people with lower values, just because of chance. And so we don't want to assume that our sample is exactly like the population. But using statistical theory, we actually can understand roughly how the population looks just from a sample. So the point of this is that we want to be able to take a sample, get statistics from it, and be able to make a conclusion about our population. We're going to rely on what's called the law of large numbers, which assures us that if we measure enough subjects, the statistic, X bar, the mean, will eventually get very close to this unknown that we have about the population. We don't know mu, and so we're getting a sample, we estimate X bar. If the sample's big enough, it's going to be very close to mu. And I know we're getting into a lot of the statistical theory here, but what we could possibly do to be able to really know what mu is we could take 1,000 samples. Just take a sample, get an X bar out of it. And we could take another sample, get another X bar, and take another sample and get another X bar. And statistical theory would suggest that the average of all of those samples would be the actual population average. So the average of the averages that we're getting in the sample would end up telling us exactly what the population average is. I want to show this example. So you have this right here. We're going to go there. It pulls up this screen, and it's going to talk about the central limit theorem. And this is one of the core theorems that allow us to really use statistical analyses to understand a population. So let's start with this example down here. So we have a population that looks like this. Perfectly normal distribution. The mean at 0. And so we have, this is what our population looks like. Let's say this is heights. And so we've turned this into a standardized score, so the average height is at 0. So these are heights. This is 3 standard deviations below 0. This is 3 above, and everything in between. So if we take a sample, this would be what it would look like if we had 100 individuals that we sampled. So it doesn't perfectly represent the population, but it's close. We can do this again. We can draw a new sample, maybe with a different sample size if it will catch up. There we go. So we have another sample. And again, it doesn't perfectly represent the population, but it's pretty close. You don't see a whole lot out in this area. You see most people here where you would expect that. And even if we have a smaller sample, let's say like 25, it's still representing our population somewhat. If it gets really big, like 200, it starts to do a really good job of representing the population. And we can run a bunch of different samples to see that. But what's important here is not what our sample looks like, but where the mean is. So what we need to understand the population, we need to understand the sample means. So if I draw one sample, we're just going to do one at a time here. Let's say our sample size is back to roughly 100. Let's draw a new sample. So every time let's say we took a sample and got a mean from the population a bunch of times. Down here it's going to plot where that mean value is. So we're going to draw another one. So all of these are just showing different mean values from these random samples that we're drawing from the population. And if we do it enough times, if we just do it over and over again, and we even can go up to 1,000 to just make this go really quick, what it ends up showing us is that the mean of our sample means is right at the population mean, and it forms a normal distribution. And it's a really tight-knit normal distribution. So from our population, we took a sample, and that sample mean, the mean from it, is going to be part of this distribution here. And that makes a lot of sense because our population was a normal distribution, so it makes sense here. But what if we change the distribution of our population to something that's not normal? As you can see here, everyone has the same probability. This is what a sample would look like. Just a random sample. But what's interesting is the distribution of the means, it's still normal. So even though the population isn't normal and our sample isn't normal, the sample means will come from a normal distribution. We can try that again with log normal. So this is a highly skewed distribution. Our sample is also really skewed. And our sample means it's still a normal distribution. Let's try exponential. Again, a very skewed sample. And our sample means it's still normal. So the point of this is that no matter what our population distribution looks like for that variable, so like if it wasn't something like heights, but GPA scores, which is a highly skewed thing, the distribution of the means, if we took many samples and got a mean from it, the means would create a normal distribution. One thing that's important with this is what happens when we change the sample size. So if we change this to go lower, what happened to our sample means? So if you were paying attention, it got way wider. So the amount that our sample means can vary is huge. That means we're less confident about where the real mean is because it could be anywhere in here. What happens if we make our sample size really big? It makes it really tight. So we're more confident about where the mean would be. So for example, no matter what this distribution is like, when we take the mean of it over using statistical theory with a sample size of 200, we would be pretty sure that the true mean out there would be somewhere between this point and this point, and would probably be right at 1. If our sample size was really small, like 1, then we would be confident that it would be somewhere between all of these points right here. So where we're confident the value would be has really become quite wide. And then you can see everything in between. So we're more confident with this, even more confident, and ultimately really confident there. So 2 things to take from this. One is it doesn't matter the distribution type of your variable. The sample means will still create a normal distribution. Second is the sample size really influences how confident we become about where the true mean is in the population using the sample means. So the mean of a sampling distribution for a sample mean is just as likely to be above or below the population mean, even if the distribution of the raw data is skewed. That means we have this nice normal distribution, and it's just as likely to be slightly above or slightly below the real mean. The standard deviation of a sampling distribution for a sample mean is smaller than the standard deviation for the population by a factor of the square root of n. Which means in order for us to understand the sampling mean, the distribution of that, we're going to have to make one additional adjustment to the standard deviation. So take this example. Let's say the population is normally distributed in this case. If the individual observations have the normal distribution, that's what this n stands for, with a mean of mu and a standard deviation of sigma. What that means is whatever these values are, it's a nice normal distribution with those values. That means the sample mean of the population of a size n has the distribution of normal with a mean of mu, the same mean, and a standard deviation of sigma divided by the square root of n. So that's going to be the distribution of the means. So in this case, the distribution here has the mean of mu, which the population mean here is 1. And the standard deviation is the standard deviation of our sample divided by the square root of n. In this case, the n is 200. What's nice that we showed is it doesn't matter if the population is skewed. It doesn't matter if it's not normal, because the sample means will still be normal. And this is thanks to this idea of the central limit theorem, which says something to this effect. When a sample size n is large, and large is not perfectly defined what that means, but often even just like somewhere above 5 to 10 individuals, the sampling distribution of the sample mean is approximately normally distributed about the mean of the population with a standard deviation less than that of the population by a factor of the square root of n. So let's go back to some examples. So let's assume the school's population of students' heights are normal with mean of 1.4 meters and a standard deviation of 0.15 meters. So we can still ask the probability of a randomly selected student is more than 1.63 meters tall. We also can ask the probability of a randomly selected sample of a certain number of students their average of being more than that. In our in-person class, we're going to go over this example. But I want to highlight that the steps that we showed to do this part, it's identical to this one, other than instead of just using the standard deviation, we're now going to use what's called the standard error. And that is just the standard deviation divided by the square root of n. So we would take the standard deviation, this value, divide by the square root of this, which the square root of 16 is 4. So it would be this value divided by 4. And now that is how you'd find your z-score. So it would be z equals this value minus this value divided by this value divided by 4. So that is now going to be our z-score. So you have a z-score for a student in this distribution, but you also can have a z-score for the sample. A sample of 16 students in this case having an average up here. So one thing to consider with this is this idea that if we knew the population values like we do here, we could say how crazy of a sample this is based on where its mean is at. So we could say, yeah, this mean is this likely to occur if this sample is really from this population. So see if you can solve this problem. We're going to talk about this in class, and we'll make sure that we answer all the questions related to it. But it's just one more step, and that step is just dividing the standard deviation to create the standard error. All right, so we're going to apply this to the cancer data set. Again, this is just an example data set. We're going to do some cleaning. This is stuff you've seen before. We're going to get the mean and standard deviation for age. We can standardize with the scale function. So in this case, we have cancer clean and our age variable. We already found out the mean and standard deviation, so we could do it by hand. So this age z is just age minus the mean divided by 12.9, which is the standard deviation. So that standardizes age. Or we can just use a scale function that'll give us the same thing. So you'll note these values are just slightly different from each other. And that's due to rounding and some possible missing values more than likely. But overall, these are going to give you the same value. The only reason why they would differ is because of rounding. This is only rounded to one decimal place, where this one would round to as many decimal places as it could. Now, one thing to note is our age variable. This is the mean and standard deviation. Our standardized version has a mean of 0. It says -0, but that's the same thing. And a standard deviation of 1. That means you standardized it. Now, it doesn't matter if we use age or age z, our distribution is going to be the same. Just the values will be different. So here it's the z-scores instead of the raw age values. But the distribution would still be the exact same because standardizing doesn't change the distribution. So for now, that's going to be it. We're going to use the statistical theory we talked about understanding sample means, when we actually get into testing hypotheses. So we're going to start with the one sample z-test is going to be the first thing. And we're going to rely on what we learned today in order to do that. Until then, please post any questions that you have, and let me know if there are certain topics that you want to cover in our in-class discussion coming up.